All right, so good morning. Let's get started. So this is the last lecture, basically, of the semester. So, and in the last sort of lecture, what I'm going to do is I'm going to try to give you an idea of what exactly the dual problem means. I'm going to try to give you an economic interpretation. So far, we know the sort of mathematical interpretation of the dual problem. So we're trying to find an upper bound on the optimal value. So that gave rise to another Alper problem, which was a dual problem. So now I'm going to try to give you a bit more insight about what exactly the dual variables mean, and you're going to need this for your project as well. Okay? So what I'm going to do is the following. So suppose that we have the usual primal dual pair of Alper problems. So the prime is a maximization problem with less than or equal to constraints and non-negative variables. And the corresponding dual will be a minimization problem with greater than or equal to constraints and non-negative variables as well. So let's assume that we have, so let X star and W star denote the optimal solutions of the primal and dual problems respectively. And we know by strong duality, the optimal values are the same in such a case. So I'm going to call it by Z star. So Z star denotes the optimal value. So I can either compute it using the primal problem, which is given by C times X star, or I can compute it using the dual problem, so which is given by W star times B. And note that if X is a basic feasible solution, then X star will be given by B inverse times del B. So we're going to have CB times B inverse B. And on the right-hand side, since W star is equal to CBB inverse, again, we have CBB inverse B on the right-hand side as well. Okay, so it's not a coincidence that these two values are the same, basically. Okay? So now what I'm going to do is I'm going to look at the left-hand side of the equality, so which gives us the objective function value, the optimal value. And I'm going to look at the right-hand side. Okay? So in particular, Z star is given by W star B. But W star B is the same as, so it's an inner product of W star with B. So I'm going to multiply the ith component of W star with the ith component of the vector B, basically, right? Right-hand side of vector B. So W star B is precisely the same as this expression, basically, right? Okay? All right, so now we're going to use very simple calculus, basically. So now think of Z star as a function of BI's, basically, okay? It's a function of right-hand side values. So, Z star is given by W1 star times B1 plus W2 star times B2 and so on and so forth. And what I'm going to do is the following. So think of Z star as a function of B1 through Bm. And remember, B1 through Bm are just the right-hand side values, basically, right, for my current constraints. So I have an m-dimensional vector. So I'm expressing Z star in terms of the BI values, basically, right? And the corresponding coefficients are given by W1 star, W2 star, and so on and so forth. So in particular, I'm taking B1, multiplying it by W1 star, taking B2, multiplying by W2 star, and so on and so forth, and I'm adding them up, and that gives me precisely the value of the optimal solution, basically, or optimal objective function value. Okay? Now, if I view Z star as a function of B1 through Bm, then I can take the derivatives of Z star with respect to these variables, right? Okay, that's exactly what I'm going to do. So we can now take the derivative of Z star with respect to right-hand side values. So in particular, let me look at the derivative with respect to B1. So this is a partial derivative of Z star with respect to B1, right? So that's the notation that we use. So does everybody remember the idea of partial derivative, basically? So if you have a function of several variables, and if you're interested in the partial derivative, then you just assume that, B1 is your only variable and everything else is a constant, basically, right? Okay, so as a result, what I'm going to do is I'm going to pretend that B2 through Bm are constants. So B1 is the only variable. And I'm going to take the derivative of Z star with respect to B1 only. Okay? So what is the derivative of Z star with respect to B1 using this expression? This can be W1 star, exactly. Okay? Similarly, what is the derivative of Z star with respect to B2? Well, it's going to be W2 star. And the derivative of Z star with respect to Bm, which is the last variable, will just be Wm star, basically, okay? So in particular, let me give you this general expression. So the derivative of Z star with respect to Bi will be equal to what, in general? Exactly. So it's going to be Wi star, and this is going to be true for all values of I, basically, okay? For all I from 1 to m. Now, let's try to understand what this means exactly. So if you recall the definition of derivative from calculus, so basically derivative is nothing but the rate of change of a function, basically, right? So, how much does my function change if I increase the corresponding variable by 1 unit, basically? That's what the information of derivative gives you, right? Okay? So in particular, if derivative is positive, then your function will increase, okay? And if derivative is negative, then your function will decrease, basically, right? So, and the reason for that is that because derivative is just nothing but it gives you the rate by which your function will change, okay? Does everybody remember that? Okay? So let me try to use that reasoning to understand this equation. So this means that if I increase Bi by 1 unit, then I'm going to expect a change of Wi star in my objective function value, basically, right? Okay? So in other words, if I look at the rate of change of Z star with respect to change in the right-hand side of the ith constraint, that's precisely the value of the dual variable. Okay? So let's try to make it a bit more clear. So if I increase the right-hand side of the ith constraint by 1 unit, so if I increase Bi by 1 unit, then I'm going to expect a change of Wi star in my objective function value, basically. Okay? So what does that mean? So that means that essentially, my dual variables actually tell me the rate of change of my objective function with respect to right-hand side values. Okay? So let me write that down. So this implies that Wi star is precisely the rate of change, of the optimal value Z star, with respect to the unit increase in the right-hand side value of the ith constraint. Of the ith primal constraint. Now let me try to make this a bit more clear or a bit more concrete. So what exactly does this mean? So suppose that the primal problem is like a production planning problem, basically. Okay, so you want to maximize your total profit. You have n different products, and you're using m different resources to produce those products, right? So we've seen such examples before. So you can think of, let's say, the first constraint as the machine time constraint. Then we have labor time constraint, and so on and so forth. Okay. So in that case, of course, Bi is nothing but the amount of resource of I that we have available, basically, right? So B1 is, for example, total number of machine hours I can use. B2 is total number of labor hours I can use, and so on and so forth. Is that clear? Okay. So now, essentially, I'm trying to maximize my total profit while actually obeying all the production requirements, and of course, non-negativity constraints as well. And suppose that I'm interested in the following question. So let's say, pretend that you're working at a company which is producing certain products, so a bunch of products, and you have certain limiting resources, okay? So as I said, it can be machine hours, man hours, and so on and so forth, basically. And you're interested in the following. So you have some budget, let's say, okay? And with that budget, you can actually increase some of your resources, okay? So for example, you can sort of buy or rent more machine hours, you can hire more labor, and so on and so forth. And the question is the following. So if you have a choice between increasing your resources, which one would you choose? Which one would be more profitable for you, basically, okay? Well, if you look at this expression right here, so this tells you exactly how much the optimal value will change if you increase your ith resource by 1 unit, basically. Okay? So in particular, if we increase the ith resource by 1 unit, then the change in the objective function will be exactly the same as the value of the dual variable. Okay? So in that case, for example, let's say I have two resources, B1 and B2. Let's say B1 is machine hours and B2 is labor hours, let's say. And suppose that W1 star is equal to 5 and W2 star is equal to 2, for instance. Okay? So which one would you choose in that case? Well, if you want to increase your objective function as much as you can, of course, you would pick the one with the largest dual variable, basically, okay? So in a sense, the dual variables tell you how important your resources are for your problem, okay? So what is the effect of each resource on your problem? And if you were to choose to increase some of your resources, which one would be most beneficial for you in terms of the objective function value? Is that clear? Okay, so let me write that down. So suppose B1 through Bm denote the available amounts of M resources for production. Okay, so in that case, of course, X star. So let X star denote the current optimal production levels. Production levels of, let's say, n products. So X star is an n-dimensional vector. And each component corresponds to production level of the corresponding product. And here comes my question. So I'm going to sort of change my question a little bit. So how much should the company be willing to pay for each unit increase in the amount of the ith resource? So this is exactly the same as BI. So now I'm changing the problem a little bit. So suppose that we have M resources, and the current available amounts are given by B1, B2, all the way up to Bm. So you can think of B1 as the number of available machine hours, B2 is the number of available man hours, labor hours, and so on and so forth. And what you want to do is the following. So you want to increase some of your resources, of course, to produce more, ideally, right? So that you're going to have more profit, basically. And the question is the following. Of course, increasing each resource actually costs some money, right? So you have to buy either a new machine, or you have to rent some machines, or you have to sort of hire more workers, and so on and so forth. And the question is the following. So, for example, let's say B1 denotes the number of machine hours that I can use right now, that I have available right now. And I want to increase that, okay? So I want to increase the value of number of machine hours. And the question is, so how much should I be willing to pay per each unit increase in the machine hour? Okay? Now, how can we answer that question? Well, I know from this expression that if I increase B1 by 1 unit, then the increase in the objective function will be given by Wi star, basically, right? So Wi star is precisely the ith component of the dual variable, okay? So as a result, if I increase the ith resource by 1 unit, my Z star will change by this much, basically, okay? And of course, if Wi star is positive, then that means that my objective function value will increase, basically, right? Okay? Well, so if I increase B1 by 1 unit, or BI by 1 unit, then I'm going to have an increase of this much in my objective function. Okay? Well, so in that case, how much should I be willing to pay to increase the ith resource? Well, think of it this way. So this is my gain, okay, by increasing the ith resource. So I'm going to look at my net gain, right? So I'm going to pay some money to increase my ith resource. And this is the sort of revenue that I'm going to get by increasing ith resource. So what is the largest amount of money that I should be willing to pay for such an increase? Well, if I pay more than this much, basically, okay, then I'm going to get only this much, but I'm going to pay more, basically, right? Okay, in that case, obviously, it doesn't make sense. okay? Because then my net gain will be negative, okay? However, if I pay less than this amount, then this is my gain, and I'm going to subtract my cost, so as a result now I'm going to have something positive, basically. Does that make sense? Okay? So what is the answer to this question then? So how much should I be willing to pay to increase the ith resource by 1 unit? Exactly. No more than this, basically, okay? So, so we should be willing to pay at most wi star, since our increase in the objective function is given by, in the objective function, is given by exactly wi star. So in other words, if I increase the ith resource by 1 unit, then my objective function value will increase by wi star units, okay? And if I pay less than wi star, of course, then my net gain will be positive, basically, right? Okay. If I pay more than wi star, then my net gain will be negative, so it doesn't make sense to increase that resource or to pay that much for increasing to increase that resource, basically. Okay. So as a result, essentially, so what this discussion means is the following. So the dual variables at the optimal solution actually have a very nice geometric meaning or economic meaning, basically. Okay. So they tell you how your optimal value will change with respect to changes in the right-hand side of the corresponding primal constraint. Okay? So if you increase B1 by 1 unit, then the rate of change in the objective function will be W1 star. Okay? If you increase B2 by 1 unit, then the rate of change in the objective function will be exactly W2 star, and so on and so forth. So as a result, for example, if you have a choice to increase your resources, okay, and if you're allowed to increase your resources by 1 unit, or if you're allowed to increase one resource by 1 unit, okay, so which one would you have chosen? Well, essentially, by looking at these expressions, of course, you're going to pick the one for which the corresponding dual variable is as large as possible, okay? Because that will give you the largest increase in the objective function, okay? Does that make sense? So let me repeat it again. So once again, if you look at these expressions, so they tell you how your optimal value will change with respect to changes in the right-hand side vector of your primal constraints, okay? So if you increase B1 by 1 unit, then the rate of change in the objective function will be W1 star. If you change B2 1 unit, then the rate of change will be W2 star, and so on and so forth. Okay? So now I'm going to ask you the following question. So if you were to choose only one resource, to increase only one resource by 1 unit, which one would you have chosen? Okay? Now this is a very simple question once you have this relationship, because essentially you want to have the largest increase in the objective function value, of course, right? By changing 1 unit in the resource, because this is a maximization problem. And it's not too hard to see that by looking at these expressions, well, I'm going to look at my largest dual variable, okay? Because I know that if I increase the corresponding constraint, right-hand side, the right-hand side of the corresponding constraint by 1 unit, then I will get the largest increase in the objective function value, basically. Is that clear? Yes.
Shouldn't we also take a look at the costs of increasing the beats?
So as I said, that brings me to this question. So, for example, if I look at the first constraint, okay, then increasing the first constraint by 1 unit will give me this much additional profit, basically, okay? And if there's a cost of increasing that resource, and if that cost is less than this number, then I'm still good, okay? That's exactly what I was trying to say here, basically, okay? But if the cost of increasing that resource is more than W1 star, then of course then my net gain will be negative, basically. Then in that case, there's no point of increasing that resource, okay? So as a result, essentially, I mean, the dual variables have two interpretations. So first of all, they tell you how the objective function value will change if you change the right-hand side of the corresponding primal constraints. So that's the first thing. The second one is that, well, if you were to pay for increase of each resource, then they tell you the largest amount you should be willing to pay as well, okay? Because as I said, I mean, if you pay more than this, then your net gain will be negative, basically, okay? So as a result, then there's no point in increasing that resource, okay? I mean, think of it this way. So if I hire, for example, a new worker, then let's say that will cost me 1,000 liras, okay? But my production level will only increase by 800, or my profit will increase by 800. Then, of course, it doesn't make sense to hire another worker, basically, right? On the other hand, if I can hire a worker for 500, and if the additional profit is 800, of course I'm better off then. Okay, that's exactly what this means. Is that clear? All right, so let me ask you another question. So suppose that the ith resource is not fully utilized in the current production plan. So what does that mean? So suppose that, for example, I have 200 machine hours, but currently I'm only using 120 in my current production level. Okay? So which means that I have like 80 hours of additional machine time that I could have used, but I cannot use right now. Okay? So question is the following. So how much would you be willing to pay per unit increase in this resource? So let me repeat the situation again. So suppose that you have a total of 200 machine hours, okay? But in your production plan, you're only using 120 hours of machine hours right now, okay? Well, how can such a thing happen? Well, I mean, think of it in the following way. So, for example, you're producing chocolate milk, for instance, okay? If you have too much chocolate and too little milk, then milk will determine how much production you can have, basically, right? So you can have an excess amount of chocolate that you cannot use, okay? So similarly, for example, if you have labor hours and machine hours, and if labor hours actually determine how much you can produce, then you may have some extra machine hours that you cannot use, basically, right? Okay? So my question is the following. So suppose that you have an extra number of machine hours that you cannot use, and so the question is, how much should you be willing to pay to increase further the number of machine hours that you're going to use? So once again, I mean, the question is the following. So suppose that you have 200 hours of machine hours, but you're only using 120, let's say. Okay? So which means that you have like 80 hours of slack that you cannot use right now. And suppose that you want to increase it further. Okay? So you want to actually have even more machine hours. So the question is, how much should you be willing to pay to increase the number of machine hours? So let me just go back to my example. So suppose that you're producing chocolate milk. Okay? So you use 1 unit of chocolate and 1 unit of milk. Okay? And let's say you have, 10 units of chocolate available, but 100 units of milk available. Okay? How much you can produce? Can you produce with these amounts? You can produce only 10, basically, right? So which means that your production level is determined by this sort of smaller resource, basically, right? Okay? So my question is the following. So if you have 10 units of chocolate and 100 units of milk, and if you want to get more milk, basically, then how much should you pay for extra milk? Well, once again, I mean, think of it this way. So if I have only 10 units of chocolates, and if I have 100 units of milk, and if I want to buy more milk, then my production level will not change, basically, right? Because it's determined by the smallest ratio. Well, here I'm in the same situation. So if I have 200 machine hours, let's say, but I'm only using 120, then if I increase my machine hours, I will still use 120, basically, okay? So which means that this resource actually is not fully utilized. So I claim that actually increasing such resource does not make sense. Does everybody agree with me on that? Okay. Well, the answer is of course, because essentially, if there's a resource that you're not fully utilizing, well, you already have an excess amount of that resource, okay? So increasing that resource does not help you at all, okay? On the other hand, you should actually try to increase a resource which is fully utilized, basically. So in my milk and chocolate example, increasing milk will be better off for you, right? So that your production level will increase. Does that make sense? Okay. So what is the answer to this question then? So how much should I be willing to pay? Well, the answer is 0, basically. Okay? Because increasing such a resource does not actually change my optimal value, okay, or optimal profit. Does everybody see that? Well, so let me try to relate it to the dual variable. So if the ith resource is not fully utilized, let me just go back to my primal problem. So that means that if I look at the ith constraint here, so the left-hand side is strictly less than the right-hand side, basically, right? Is that clear? So if the ith resource is not fully utilized, that means that, so bi is the amount of available resource, okay? And the ith component of this vector is how much we're using that resource. So as a result, there's going to be a positive difference between the two. Is that clear?
Yes.
Okay. So which means that the right-hand side will be strictly greater than the left-hand side for that constraint. Okay. Now let's recall complementary slackness property. Well, if that is the case, then what can I say about the ith dual variable? So the ith dual variable is equal to 0, basically, right? So remember, if the left-hand side of a constraint is strictly less than the right-hand side, then the corresponding dual variable should be equal to 0. Well, that's exactly how much we should be willing to pay again. Okay? So as a result, if I'm not fully utilizing a particular resource, then I should pay 0 to increase that resource, basically. Okay? But for such a resource, then, as I said, the corresponding dual variable is exactly equal to 0 by complementary slackness property. Does everybody see that? Okay? So in this case, so this implies that Wi star is equal to 0 by complementary slackness. So this implies that we should be willing to pay 0. So in other words, increasing the ith resource further does not actually give you any extra profit. Okay? And that makes quite, perfect sense because, as I said, that's not your limiting resource, basically. Okay? So you should be worried about your limiting resources because only increasing those resources will actually increase your production and your profit as well, accordingly. Is that clear? Questions? So as a result, please keep this in mind, and I think one of the questions in your projects is related to this one. So if you were willing to choose to increase the right-hand side of a particular constraint, which one would you have chosen? Well, so since you want to increase Z star as much as possible, obviously you're going to pick a constraint for which the corresponding dual variable is as large as possible. Okay? So that's the answer to one of your questions in the project. Any questions about this? All right, so that actually finishes the material for IE-202. What I'm going to do is I'm going to solve a couple of problems, which will be a sort of preparation for the final exam as well, unless there are any questions about this. Yes?
About the last question, he said that I must be equal to 0. But if we have a resource to increase one of the constraints right-hand side, can we choose the second constraint instead of one?
If we have a choice in terms of...
Demek istediğim şuydu. Mesela işte az önce dedik labor hani eğer bizim şeyimizi belirliyorsa hani ikinci fazla olacağı için utilize olmayacak, onu arttırmamızın bir anlamı yok.
Exactly.
Ama biz burada hani labor arttırabiliriz. Yani onu nasıl şey yapacağız?
Well, so let me just go back to this example. So now again, by complementary slackness, for example, if Wi star is positive, right? So that means that the corresponding primal constraint should be satisfied with equality. Okay? So which means that if Wi star is positive, then the corresponding resource should necessarily be fully utilized. Okay? So as a result, increasing a constraint for which the corresponding dual variable is positive actually makes sense in that case. Okay? Because if Wi star is positive, then that means that I should be using the ith resource fully, basically. Okay? And then among all resources that I'm using fully, or utilizing fully, which one should I increase? Then that depends on the values of my corresponding dual variables. Okay? So what I'm trying to say is the following in terms of the last question. So in an LP problem, if you have a constraint which is satisfied with strict inequality at the optimal solution, then increasing the right-hand side of that constraint does not help you at all. So that's essentially what I'm saying. Okay? I mean, in terms of picture, think of it in the following way. So in 2 dimensions, let's say this is my feasible region. Okay? Let's say this is my optimal solution, X star. Now, what I'm interested in is the following. So if I change the right-hand side, for example, if I look at this constraint, okay? So X star satisfies this constraint with strict inequality, basically, right? Because X star is not on this constraint. So changing the right-hand side vector b for this constraint basically means that I'm actually either moving it in this direction or in this direction, okay, depending on whether I'm increasing or decreasing b. So as a result, if I make small changes, then of course x star will not be affected at all, okay? On the other hand, for example, these two resources are fully utilized at the solution. So if I change these constraints, then x star will change, and accordingly my optimal value will also change, okay? So that's essentially what the sort of analysis tells you here. Is that clear now? Okay? All right, so then let me just do a couple exercises in the last 20 minutes or so. So these are the problems from the final exam of last year, I think. Okay? So suppose that we have the following simplex tableau. So I'm given some numbers and some letters actually, 0, 0C, 3 and 14. Then I have x1 here, so 0, 1, minus 2, 0, 4, 0, 3, 1. Then I have 0, 0, minus 1, 1, 5, 0, 2 and 4. And finally, I have x3 here and x5 here. So 0, 0D, 0, 7, 1, minus 5, and right-hand side value is E. So let me just circle the letters. So I have A, B, C, D, and E. So suppose that this is a simplex tableau of a maximization LP problem, okay? So simplex tableau of a maximization LP problem. So now I'm going to try to ask some questions related to this simplex tableau. Okay. So obviously, I mean, there are some letters here, okay, instead of numbers. The first question is the following. So what are the conditions on A through E such that the tableau is optimal and there is a unique optimal solution? So what are the conditions that should be satisfied by each of these letters, A, B, C, D, E, such that the current tableau is optimal and there's a unique optimal solution? In other words, what are the possible values A through E can take so that the current tableau will be optimal and there's going to be a unique optimal solution? Okay? So what are the conditions that should be satisfied by A, B, C, D, and E, basically? So, okay, let's start with A. Now, remember, x1 is a basic variable, and we know that for every basic variable, there should be only one non-zero. Everything else should be 0, so A should be 0. Otherwise, tableau will not be in proper form. Okay? So, what about B? Well, remember, B is the row 0 coefficient of x2, basically. If B were negative, then this solution cannot be optimal, basically, right? Okay? If B is equal to 0, what does that mean? Well, x2 is a non-basic variable. If B is equal to 0, then I can enter x2 and continue, and that will give me an alternative optimal solution, basically, right? But what I'm interested in is a unique optimal solution. So what does that imply on B? So B should be strictly positive. That's good. What can I say about C? Once again, so x5 is a basic variable, so C should be equal to 0. What about D? What about D? Well, so if you think about this a little bit, so D is the entry underneath x2 in row 3, basically, okay? And at this stage, of course, D does not play any role at all. okay, in the solution, okay? Well, once again, so D does not play any role at this stage. So what does that mean? So D can be anything basically, okay? So there are no restrictions on D. So you can either say D is free, or you can just say that D can be any real number, okay? And finally, what about E? Well, so E is the right-hand side value of x5, okay? And for primal feasibility, everything here should be non-negative, of course, okay? So what does that imply about E, basically? Greater or equal to 0, okay? So E can be equal to 0, in which case the solution will be degenerate, but I don't care, okay? So all I need is the fact that the current solution should be optimal, and there should be a unique solution. So unique optimal solution is determined by row zero coefficients, okay? And optimality requires feasibility, so that all the right-hand side values should be non-negative. Is that clear? Yes. All right, so let me continue with the next example then. Any questions about this? So again, so give the conditions on A through E such that, so I'm not going to write the first part, such that the tableau is final, the tableau is optimal, the tableau is optimal, and there are alternate solutions. Alternate optimal. Mm-hmm.
Yani sıfır olduğu için bizim yine mantıklı solution'ımız yok mu? Ondan diyecek. Ve eğer bu tabloya göre unique arıyorsak. O zaman yani...
Yes, I made a mistake, yes. Okay, thank you. Yes, you're right. So basically, row zero coefficient of x4 should be positive. Okay, so now I'm looking at the next question. So what are the conditions on A through E such that the current tableau is optimal, but there are alternate optimal solutions? Okay. Well, so let me again start with A. What is the condition on A? Well, A should always be equal to 0. Okay, if this is a simplex tableau, A should always be equal to 0. What about B? Well, so I want alternate optimal solutions here, okay? So my non-basic variables are x4 and x6. If I increase x4, then the objective function value will go down. If I increase x6 again, it will go down, okay? So what I want to do is I want to be able to enter a non-basic variable so that the optimal value will not change, okay? So B should be equal to 0 basically, okay? What about C? Well, C is always 0, again, that never changes. What about D? Or should it? All right, so now let's think about the following cases. So if D is positive, then obviously the only eligible row will be this one for minimum ratio test. I'm going to enter x2 and x5 will leave, and I'm going to continue. So what happens if D is equal to 0? Well, if D is equal to 0, or if D is negative basically, if D is not positive, let's say, then I can increase x2, but none of the variables will leave the basis basically, okay? So what does that mean? Well, essentially that means the following. So we have done such examples before. You will be in a situation such as this one, okay? So this is your optimal solution, let's say, okay? And then let's say C actually points in this direction, okay? So this is your C vector for maximization problem, so that, you know, everything here will be an optimal solution basically, okay? So if D is negative or equal to 0, that means that you can try to increase one of the variables, but there's no blocking constraint, so you will always actually lie on this line basically, okay? So which means that you will still have alternate optimal solutions, okay? And since the objective function value will not change, you can have an infinite number of optimal solutions basically, okay? So as a result, again, there's no restriction on D, okay? So of course, I mean, the point of this question is to test whether you really understand the simplex method, okay? So as a result, D should be free. Sorry? Well, if you recall, if you look at your notes earlier, so we said that in that case you can find parametric solutions. So we said that x2 can be equal to a, then x1 will change depending on a, x2 will change depending on a, and so on and so forth, okay? So you'll find a whole bunch of different solutions, basically, okay? What about E? So what can I say about E? Well, by the same reasoning, by primal feasibility, E should be non-negative, okay? Any questions about this? So is it clear that YD should be free? Okay. All right, so let me look at part C, or part 3. So such that, again, what are the conditions on A through E such that the simplex method determines an unbounded solution from this tableau. So what are the conditions on A through E such that the simplex method determines an unbounded optimal solution from this tableau? So once again, let me start with A. So what are the conditions on A? Well, A should always be 0, okay, regardless of what the question is. So what about B now? Well, I want to make sure that the simplex method will determine that the problem is unbounded, okay? So which means that the current solution cannot be optimal, okay? So which means that there should be an entering variable, but there should be no leaving variable, basically, right? And since this is a maximization problem, so my non-basic variables are x2, x4, and x6. x4 and x6 cannot enter the basis, okay? So the only potential candidate is x2, okay? When can x2 enter the basis? Well, if the value of b is negative, basically, okay? So b should be strictly less than 0, so that increasing x2 will increase my objective function value, okay? But at the same time, so hold on. Let me just continue with C. What about C? Well, C again is always equal to 0. Again, independent of what the question is. Now, what about D? Well, I want to increase x2, but I want to make sure that there is no leaving variable, basically, right? Okay. So the first two rows are not eligible for the minimum ratio test already. So the only potentially eligible row will be this one. And I want to make sure that this row will not be eligible either. Okay. So it's actually less than or equal to 0, right? So if t is equal to 0 or negative, then that means that row 3 also is not eligible, so which means that the problem will be unbounded, basically, okay? And what about E? Well, E again should be non-negative, okay? And finally, last part. So part 4. So what are the conditions on A through E such that the current tableau is degenerate, or current BFS is degenerate, but not necessarily optimal. So let's just quickly do this again. So now I want to make sure that the current solution is degenerate. May or may not be optimal, I don't care. Okay. Let me start with A. So what's the condition on A? 0. Now what about B? Well, since I don't care whether the solution is optimal or not, B can be anything, basically, okay? So if B is positive, then obviously it's optimal. If B is 0, then there are alternate optimum solutions. Then if B is negative, then the solution cannot be optimal. But I don't really care, so as a result, B can be anything. Okay? What about C? C is always 0. What about D? Again, D can be anything because I don't really have any restrictions, whether the problem is unbounded or not. What about E?
0.
So this is the important part. E has to be equal to 0. Okay? So remember, by definition of degeneracy, there should be at least one basic variable whose value is equal to 0. And since x1 and x3 are different from 0, then the only remaining variable, x5, should be equal to 0. Otherwise, the solution will not be degenerate. Okay? Did you like the questions? Okay, good. So let me just give you one more example quickly. Okay, again, this is another question from the final exam. So suppose that we have the following problem. Maximize minus x1 minus x2 plus 4x3. Subject to x1 plus x2 plus 2x3 is less than or equal to 9. Then x1 plus x2 minus x3 is less than or equal to 2. And minus x1 plus xt plus x2 plus x3 is less than or equal to 4. And all variables are non-negative. So suppose that we are given this LP problem. Okay. And then I'm going to give you a simplex tableau corresponding to this problem. So row 0 looks like the following. So 1. Then I'm going to have A, B, C, D, E, F, G. Then I have x1, x5, and x3 as my basic variables. 0, 0, 0. Here I have H, I, J. The right-hand side is K. L, M, N. Right-hand side is O. P, Q, R. And the right-hand side is S. Okay? So this is not 0. This is just the letter O. Then I have 1 over 3, 0, minus 2 over 3, 0, 1, 1. And 1 over 3, 0, 1 over 3. So we're only given basically these 3 by 3 part, okay? And everything else is unknown right now. And our task is to find what those numbers are, okay? So the first part of the problem is as follows. So find B inverse and CB. Of course, I mean, I'm going to assume that x4, x5, and x6 are the select variables corresponding to first, second, and third constraints respectively, okay? All right, so what is my B inverse for this problem? Well, I mean, we have done this so many times that, I mean, I cannot really forgive you if you make a mistake on this one, okay? So remember, the 3 by 3 part underneath the select variables always gives me B inverse, right? Okay? So as a result, my B inverse will simply given by, well, I'm not going to write it, but so this is my B inverse. What is my CB vector? Well, remember CB was the cost coefficients of basic variables. Okay? Yes. And what are my basic variables? X1, X5, and X3, basically. What are their cost coefficients? So I have minus 1, followed by the cost coefficient of X5, but X5 is a select variable, so its cost coefficient is 0, 0, followed by the cost coefficient of X3, which is equal to 4, basically, okay? All right, so the second part of the question is as follows. So find all the values of A through S, basically, okay? So this is another question to test your understanding of the simplex method, basically. All right, so what can I start with, for instance? So we can compute the values of basic variables. How can I do that? So how can I compute these values? What is my little b? It's actually 924 basically, right? So this is my little b. Okay? And I know what b inverse is. If I multiply b inverse by little b, I can get the values KOS, right? Okay? All right, so how about this one right here? How can I find the value of g? So I know what CB is. I just computed B inverse B. So CB times B inverse B will give me this number right here. Okay? What about these values? DEF. CB B inverse. I know what CB is. I know what B inverse is. So I get exact CB B inverse from here. Okay? All right, so I still have 12 more unknowns, basically. Okay? Now, here is one thing that you can use. X1 is a basic variable, basically, right? Okay? So X1 is a basic variable in the first column. So what can I say about the values of A, H, L, and P? Exactly. So I should have 0, 1, 0, 0 here, because otherwise X1 cannot be a basic variable, okay? Okay? What can I say about the column underneath X3? Well, again, X3 is a basic variable. So as a result, I'm going to have 0, 0, 0, 1. Okay? What about B, I, M, and Q? Well, remember, so this is nothing but B inverse times the second column of A, basically, right? So I'm going to multiply B inverse from the left and the second column, which is given by 1, 1, 1. So B inverse times 1, 1, 1 is exactly this column right here. Do you remember that? Okay. So as a result, this is precisely B inverse times A2. But A2 is equal to 1, 1, 1. So I'm going to have B inverse times 1, 1, 1, basically. Okay. Where does 1, 1, 1 come from? Well, it comes from the column of X2. Okay. Finally, what about B? Well, remember, so that was given by CB B inverse A2 minus C2, basically, right? Okay. And I know what CB B inverse is. I know what A2 is. I know what C2 is. C2 is just equal to minus 1. And if you compute this, you will get the number corresponding to value B, basically, okay? So, I mean, this example basically tells you, this question tells you that you can compute all the entries of the simplex tableau if you know your current basis inverse and your current CB, okay? If you know these two components, then you can compute everything in the tableau, okay? Any questions? All right, so good luck in your final exams, okay?